Urban growth today is happening faster than ever before. Cities are expanding at an unprecedented scale, transforming landscapes, infrastructure, transportation systems, and the way people live. For governments, planners, and decision-makers, understanding how cities evolve over time is no longer optional. It has become essential. Traditionally, urban growth analysis relies heavily on historical satellite imagery, aerial photography, and multi-temporal geospatial datasets. Using advanced image processing, feature extraction, and spatial analysis techniques, organizations can detect and monitor how urban environments change across years and decades. This includes tracking the expansion of buildings, road networks, green spaces, and land use patterns across the city. But for this particular demonstration, historical imagery and temporal datasets were not available. So instead of stopping there, we approached the challenge differently. We developed an alternative spatial simulation methodology using open-source building footprint data. Because the building data itself did not contain historical construction years, we created a spatial growth model capable of approximating how urban expansion may have progressed over time. To achieve this, we considered the historical center of Riyadh as the original urban core, representing the earliest stage of development. From that central origin point, we generated progressive spatial zones extending outward across the city. As distance from the urban core increases, estimated development years gradually increase as well. This creates a realistic simulation of how cities naturally expand outward over time through urban sprawl. The result is a dynamic temporal model where every individual building footprint becomes associated with a simulated development timeline. This allows us to visualize urban expansion year by year, revealing how the city may have evolved spatially across time. And this is where the experience becomes even more powerful. Instead of limiting urban analytics to GIS specialists and technical users, we can now introduce an AI-driven interaction layer directly on top of the spatial platform, an intelligent assistant capable of understanding maps, spatial layers, urban patterns, analytical results, and geographic context. Rather than building complex dashboards, configuring filters, or running technical GIS workflows manually, users can simply interact with the system conversationally using natural language. For example, show urban sprawl from 1910 to 2020, update analysis range from 1950 to 2020, create cumulative urban growth chart, generate decade distribution chart, create yearly trend analysis chart, generate analytical reports. Instead of searching through layers and tools, the system understands intent, transforms requests into spatial analysis, and delivers insights instantly. What becomes especially valuable here is that the experience moves beyond simple visualization into knowledge discovery and urban intelligence. As the platform continues analyzing spatial patterns across time, it can progressively improve analytical understanding based on local urban characteristics, regional development behavior, and historical expansion trends. Through this type of spatial intelligence, organizations can begin understanding the direction of urban sprawl, the speed of city expansion, areas experiencing concentrated development pressure, regions lacking sufficient service coverage, and locations where urban growth may become increasingly unbalanced over time. One of the most important insights in urban sprawl analysis is understanding directional growth behavior. When urban expansion becomes heavily concentrated toward a single corridor or geographic direction, infrastructure delivery and public service expansion become increasingly difficult, expensive, and inefficient. This impacts transportation systems, water distribution, electricity networks, telecommunications, and overall accessibility to public services. However, when urban growth is more balanced spatially, cities can significantly improve infrastructure efficiency, optimize service distribution, and support more sustainable long-term development strategies. And once we establish this level of urban understanding, the next step becomes connecting urban intelligence directly with future planning workflows. This is where the integration between urban growth analysis and urban planning becomes extremely valuable. Organizations can begin connecting spatial intelligence with land use planning, residential subdivision strategies, commercial zoning evaluation, infrastructure expansion studies, government housing initiatives, and smart growth planning approaches. Suitability analysis workflows can also help identify the most appropriate locations for future developments based on multiple planning criteria such as accessibility, population distribution, existing infrastructure, service coverage, environmental considerations, and urban development priorities. For example, planners can evaluate the optimal locations for future schools, healthcare facilities, residential expansion zones, commercial districts, public amenities and parks, and long-term infrastructure investment priorities. Scenario-based planning workflows can then compare multiple development strategies to better understand accessibility impacts, infrastructure demand, service distribution efficiency, and long-term sustainability outcomes. Planners can visualize projects spatially, evaluate zoning and land use scenarios, analyze development proposals, monitor infrastructure impacts, and better understand how future developments may affect surrounding communities. The goal is no longer just to monitor urban expansion. The goal is to create smarter cities, more sustainable infrastructure, better planning decisions, stronger collaboration, and a future where spatial intelligence and AI work together to transform how cities are understood, planned, and developed. This is not just urban visualization anymore. This is the future of AI-powered urban intelligence.